Hello everyone, and welcome back to this series on multivariable calculus. So far we have discussed how to do differentiation in higher dimensional spaces, and we've also discussed how to do Taylor series and Taylor approximations in higher dimensional spaces. Now we get to explore how to do integration in higher dimensional Euclidean spaces today. So let's just quickly go over what we mean by integration. So you probably are already familiar with statements like the integral from minus infinity to infinity of 1 over 1 plus x squared dx and what this means geometrically. So pretty much what we have here is we have some curve. In this case it's symmetric about the y-axis. And what we want is to find the area under the curve all the way from x is equal to minus infinity to x is equal to positive infinity. And that area, hopefully, is some finite real number. In this case, this integral definitely does converge because, firstly, the antiderivative of 1 over 1 plus x squared is the inverse tangent function. And then we need to evaluate this as x goes to infinity and x goes to minus infinity in the limit. You should know that arctangent has horizontal asymptotes of pi over 2 and minus pi over 2. So we clearly see that this is just going to be equal to just pi. All right, so what are we exactly doing? So what we're doing is we integrate over some domain, and we're going to write the domain D in this case as the set of all x values such that minus infinity is less than x is less than positive infinity, which in this case obviously is the set of R, to get some area. Let's call that area A, where x, or dx moreover, is corresponding to the length of our little mini rectangles, and y, aka f of x, is corresponding to the height of our little mini rectangles. And this is obviously motivated from the construction of the Riemann integral using Riemann sums. Therefore, we can write our integral as a is equal to the integral over domain D of f of x dx. Right, so this is our one-dimensional integral from single variable calculus. So now what we're going to do is we're going to try and extend f to higher dimensional domains. In particular, let's suppose that f, instead of sending r to r, let's send r2 to r. So now we're going to have a two-dimensional domain. And let's suppose we want to integrate over, or integrate f over some domain D, subset of R2. So what is that going to look like? So what we're going to have here is a two-dimensional, I'll try my best to draw a three-dimensional surface here. So we have some domain D for which we're interested in. So this is going to be equal to D. And then we're going to have some surface that's sort of floating above this domain. So obviously these points are going to project to the surface somewhere, right? So for example, if we look at this little region, then what you're going to have here is some surface, right? And that surface is going to have some volume underneath it, right? So there's going to be some volume underneath that box. In this case, it almost looks like a cube, but our goal is to find the volume of this region, right? So our goal is to find the volume of this region. So the volume is equal to the double integral over the surface of this function on that particular domain D. All right, so this is the volume under the surface, which is analogous to area under the curve in one-dimensional domain. Right? So volume under the surface, area under the curve. And how do you find volume of a rectangular prism in 3 dimensions? Well, volume is going to be equal to length times width, and now we're going to have times height. So this L times W, that's going to represent our area that we were finding before. And now we have our H, which is going to correspond to height. And this is going to be generated from our function fxy. Right? So therefore, in terms of notation, what we're going to have here is v is going to be equal to the double integral, since we're going over a two-dimensional domain, of d of fxy dA. right? And some people will write dA as dx times dy, right? So where dA is dx times dy, or you can say it's equal to dy times dx, since those infinitesimals will indeed commute. So we can write this in a couple ways, of course. We can write this as v is equal to the integral over the x domain followed by the y domain, and then fxy dy dx. I'm going to be putting little variables inside of the little integral signs so you know exactly which integral corresponds to what. Some people won't do this though, because usually they will match them sort of like parentheses and brackets using the same notation. So you can also re-represent this as the integral over y and then the integral over x of fxy dx dy, and again make sure that your integrals match going from inwards to outwards. All right, so this is what we refer to as a double integral. Some people will also call it a volume integral. So let's actually go through a very basic example. Let's suppose that our two-dimensional domain D is going to be the set of all points xy such that, and xy is going to be belonging to R2, such that 0 is less than or equal to x less than or equal to 2, and 0 less than or equal to y less than or equal to 3. So let's first off start off by graphing this domain, just to see what type of area we are integrating over. So x goes from 1 to 2, and then y goes from 1 to 3, 0 to 3. So what we're going to be having is this region, right? So D is a rectangle. D is a rectangle. So we're going to be integrating over a rectangular region, and double integrals are actually very, very easy to do when your domain is rectangular. All right. So let's assume that f is going to map R2 to R, and let's define fxy to be equal to 2xy plus 3y squared plus 1. So regardless of the function defined here, pretty much integrating over that rectangular region should be easy as long as it's defined there, right? And as long as the antiderivatives are pretty nice too. So what are we going to have? So the volume is going to be equal to the double integral over D of fxy dA. So we can do the x integral first. So x ranges from 0 to 2, followed by the y integral, which is going to range from 0 to 3, of 2xy plus 3y squared plus 1 dy dx. So that's one way you could go about it. Or you could say that this is the integral from 0 to 3 for y, and then the integral from 0 to 2 for x of 2xy plus 3y squared plus 1 dx dy. You should be able to see that these both will give you the same answer. I'll do one of them for you, and I leave the other one as an exercise for you, right? But I'm going to do this second one. So what is this going to be? So we're going to have the integral from 0 to 3, and that's going to be a y integral. And then we're going to be looking at this integral here. Note that this is with respect to x, so everything with y is just a constant as far as x is concerned. So the antiderivative of 2xy, where y is just a number, is going to be equal to x squared y. So we're going to have x squared y. 3y squared is just a number, so that's going to be equal to 3xy squared. And then the integral of 1 is just going to be equal to x. And then what are we going to do? Well, we're going to send x to 2, send x to 0, and after that, we're going to integrate with respect to y. All right, so once we're done here, what are we going to have? So take a moment and evaluate this. So we're going to have 2 squared, which is going to be equal to 4. So the integral from 0 to 3 of 4y, and then 2 times 3, that's going to be equal to 6y squared, and then we're going to have plus 2. Right? And now we have a single variable integral, which is actually pretty nice. Let's just evaluate this. So it's going to be equal to the antiderivative of 4y, so that's going to be equal to 2y squared, and then we're going to have divided by 3, so it's going to be 2y cubed plus 2y, and then we're going to evaluate this as y goes to 3, as y goes to 0. So that's going to be equal to 3 squared. 9 times 2 is 18, plus 3 times 3 is 9, times 3 is 27, times 2 is 54, and then 3 times 2 is going to be equal to 6. 54 plus 6 is going to be equal to 60, plus 18 is going to be equal to 78. Right? So that's going to be equal to the double integral of 2xy plus 3 squared plus 1 over that rectangular region as defined before. And again, it should not matter the order for which you do this, since we are on a rectangular region. In some sense, y doesn't really depend on x, nor does x really depend on y. Now let's see how we do double integration over regions that is a little bit more complex compared to rectangles. For our next example, let's assume that our domain is the set of all points x, y, satisfying x squared plus y squared is less than or equal to 1. You should immediately be able to recognize this domain since it's such a famous shape. In particular, it's just the unit circle boundary and also its interior. So pretty much this is the region we are integrating over, including the boundary. So it's very important compared to the last example with our rectangle domain that x and y are now jointly connected. Because if x changes, y will have to change as well in order for this inequality to be satisfied. In particular, y can be found by solving for y as this plus or minus the square root of 1 minus x squared. So if I were to say when x is equal to -1, where does y range from? Obviously that's going to be 0 to 0. When x is equal to 0, where does y range from? Obviously that's going to be -1 to 1. But if I were to pick up any point x, notice that the value of y will change because in some sense as x changes, y changes as well. Okay, so if this is the case, how would we write our volume integral? So v, generally speaking, is the integral over d of some function for which can be defined up to your choosing. This is going to be equal to what? So let's integrate from 1 to 1 with respect to x, and then let's let y depend on x, but you could do it the other way around if you really wanted to. So this is going to be the integral of x from -1 to 1. So x is now going to be chosen. So now, since x is chosen, for example, here, then y is going to range from there to there, which is going to be from minus the square root of 1 minus x squared to the positive square root of 1 minus x squared. So that's going to be minus square root 1 minus x squared to positive square root of 1 minus x squared of our function fxy dy dx, right? So that's going to be our y integral. All right, so that's going to be your general setup for an integral of this type. And now we just need to define a function of our choosing. So let's assume that f is defined as r2 to r. And let's define it, let's just do a very basic structure. Let's do a plane. Let's do x plus 2y. So I want you to try and find, maybe pause this video and try it on your own, to find the area or the volume underneath this linear plane over the unit circle. So what is v going to be? So v is going to be equal to, so we can integrate over x and then 2y if we want to. So we can integrate over d for x and dA, and then we can integrate over d for 2y with respect to a as well. Right? So let's focus on this first integral, and then we can focus on this second integral. So integral number 1, what do we have? So we have the integral from -1 to 1, and then the integral from minus the square root of 1 minus x squared to positive square root of 1 minus x squared. So positive square root of 1 minus x squared of x dy dx. So with respect to y, x is just a constant, so we can write this as the integral from -1 to 1 of xy. And then y is going to range from the upper limit to the lower limit and then subtract. So we can write that as the square root of 1 minus x squared minus negative square root of 1 minus x squared, and then we're going to have dx. And this is going to be equal to the integral from -1 to 1 of 2x times the square root of 1 minus x squared dx. Now, a couple little observational things. Let's call this function gx for a moment. And notice that g of minus x is equal to minus g of x. Right? So what is the significance about this? So sine is another function that is famous for satisfying this property. because notice that we're going from -1 to 1 for this function, and it's symmetric about the origin, which means the area to the right is going to be something, the area to the left is going to be something, and they're going to have the same but opposite values. So when we add them two together, they will cancel out. So that means this is going to be equal to 0, right? So this is just an integral of an odd function over symmetric interval always equals 0. This is a very beautiful result for integrals, and higher order integration obviously satisfies this property because we do one integral at a time. Right? So this means that our volume is entirely dictated by that second integral. So let's see if we can figure out what this is going to be equal to. So this is going to be, again, the integral from -1 to 1, and then the integral from minus the square root of 1 minus x squared to positive square root of 1 minus x squared, and then y dy dx. So again, notice that we have a function of y, right? So that's like y is equal to x or x is equal to y, which is, again, symmetric about the origin, and we're going from minus something to positive something, where those somethings are equal to each other. So here we have minus the square root of 1 minus x squared, and here we have positive square root of 1 minus x squared. We're doing this area, that area, and obviously they're going to be the same but opposite numbers. Therefore, this interior integral is another odd function integrated on a symmetric domain. So therefore, this is going to be the integral from -1 to 1 of 0 dx, which will be equal to 0. So therefore, the volume of this surface will be equal to 0, which means that our plane with respect to volume is symmetric with respect to this chosen domain of a unit circle. So therefore, v is equal to the double integral of d of this particular fxy. dA will be equal to 0 for this case. Although it does come out to 0, some people will be like, oh, that's kind of boring, but 0 is just as significant as any other volume that you may encounter, although it does have some special properties in application. So up to this stage, we know how to do double integrals over rectangular domains. That's the easiest of them all. And we also know how to do double integration over other domains where y depends on x or x depends on y, or vice versa. Yes, the regions can be quite complex, where the definition or the relation or dependency between x and y are very complicated to express in terms of functions, which obviously will motivate using, for example, polar coordinates, or maybe parametric coordinates, or cylindrical coordinates, or other coordinate systems to better represent that area and or boundary. But for now, we're just going to assume that you're comfortable with rectangular regions and y as a function of x type of regions, like we did in the last two examples. And we're just going to end this video with another example of how multiple integration can be used to solve single variable integration problems. Some people will think like, oh, well, isn't double integrals more complicated than single integrals? Actually, no, because, well, sometimes. But in this case, we have the integral from 0 to infinity of sine x over x dx. And some people may recognize this if you watch my non-elementary primitives video for integrals, because not every function is an elementary primitive, that this is just equal to the limit as n goes to infinity of the sine of n over n function, or the sine integral, right? Because this is just the integral from 0 to n of sine x over x dx. And you might remember that this character is just the limit as n goes to infinity of psi of n, which has a very interesting looking graph. It has a horizontal asymptote of pi over 2, or an asymptotic periodic asymptote, plus or minus pi over 2 on the left and right. So this integral is equal to pi over 2. But how can you prove it without using fancy techniques such as Laplace transforms or Fourier transforms, and maybe you even know those? But you can actually find this using multiple integration. Now, although this is a special case of how you can use multiple integration for this problem, other single variable integrals can also be calculated via this multiple integration, I guess you could call it, trick. So let's just note a couple things here. So if I asked you to find the integral from 0 to infinity of minus e to the minus xy with respect to y, you're going to be like, oh, well, x is just a constant, so I can treat it as 1. And you would be correct. So minus 1 over x times e to the minus xy. And then here, y is going to go to infinity. Y is going to go to 0. Let's assume that x is a positive number. That means this is going to go to where? So this is going to go to 0, that's going to go to 1, and we're just left with 1 over x, right? So the integral from 0 to infinity of e to the minus xy dy is just the function 1 over x. So some people can be like, oh, how do you define the reciprocal function? So the reciprocal function could be defined as the integral from 0 to infinity of e to the minus xy dy. And you're like, well, that's kind of strange. Why would you ever define a rational function like that? Well, keep in mind the natural log function can also be defined as the integral from 1 to x of 1 over t dt. So it's actually not that much of an absurd fact of why you would define a function in terms of an integral, because integrals can always be approximated, for example, via Riemann sums and stuff like that. Right? So we have 1 over x is definable as this improper integral from 0 to infinity of e to the minus xy, provided that x is a positive number. So now let's just tuck that into the back of our mind temporarily, and let's revisit the integral that we're interested in finding. So this is the integral from 0 to infinity. I'm going to write sine x over x in a very strange way. I'm going to write it as 1 over x times the sine of x dx, and you may immediately already see why I want to do that. So note here that x is a positive number, non-inclusive of 0. I can avoid it using right rectangle approximations for Riemann sums. And I'm going to define d to be equal to the set of all points xy in R2, of course, such that x is positive and y is positive as well. Right? So how can I re-represent this integral? So keep in mind, I can write 1 over x as that integral that I mentioned before. So I can write this as the integral from 0 to infinity of the integral from 0 to infinity of e to the minus xy dy, and then we're going to have sine of x dx. So notice that I have a double integral here, 0 to infinity, 0 to infinity, so that's precisely the domain D, and then we have e minus xy dy dx, and since the domains are the same when we have dx and dy, I can write it as dy dx. Either way is perfectly fine. So therefore the integral that we want to find is actually the integral, double integral of over d of the function e to the minus xy sine of x dA. So this is another way of writing the integral that we're interested in finding. Now let's see if we can figure out what that integral actually is equal to. So remember, we can write sine in terms of complex exponentials. This is 1 over 2i times e to the minus ix minus, actually plus ix, and then e to the minus ix. And if you don't remember this identity, use Taylor series to prove it if you want to, right? But this is a very important identity. So this is going to be equal to what? So 1 over 2i is just a constant, so I can factor it out. So we're going to have 1 over 2i times the double integral over d, and then we're going to have e to the minus xy times e to the ix minus e to the minus ix with respect to x, followed by the integral with respect to y. Right? Now I'm going to distribute my exponentials. This actually motivated the introduction of these exponentials because I now can combine those exponents, and I know the integral of e to the ax. That's just a basic antiderivative. So this is actually going to be re-represented as 1 over 2i times the double integral over d, and I can write this as e to the power of y minus I x, and then minus e to the minus y plus I x dx dy. Again, I'm going to be doing the x integral first, followed by the y. Okay? So that's the integral from 0 to infinity. Keep that in mind, but the other one is as well. So we're going to be left with what? So we're going to be left with 1 over 2i times the integral from 0 to infinity, and that's a y integral, keep that in mind. And this is going to be equal to 1 over y minus I, because the other one goes to 0, and this one's just going to go to that constant, 1 times that constant, and then 1 minus 1 over y plus I, and then dy. All right? I highly recommend you verify that if you're not comfortable with that statement. All right, so once we have that, now we have two fractions, which we can easily get a common denominator for. So I can write this as 1 over 2I times the integral from 0 to infinity of y plus I minus y minus I all over y minus I, y plus I, and that's just a difference of two perfect squares on bottom, in particular y squared minus I squared. I squared is equal to -1, so that's y squared plus 1 on the bottom. So we're going to be left with 1 over 2I times the integral from 0 to infinity of y squared plus 1. On the top, we're going to have y minus y. They cancel. I minus negative I, that's going to be equal to 2I. And what happens with that 2I? It cancels with the 2I in the front. Right? So now we're just left with the integral from 0 to infinity of 1 over 1 plus y squared. And who is this? Well, this looks like half of the integral from minus infinity to infinity of 1 over 1 plus y squared. Right? So that's half of the entire region that we found earlier. So that means this is just equal to pi over 2. Right? So isn't that beautiful? We get the same exact answer as we did before. So therefore, the integral from 0 to infinity of sine of x over x dx, which again, if you know the sine integral function, so this is limit as x goes to infinity of psi of x, this is equal to pi over 2, which we've now proven using this very beautiful, I think, to me at least, multiple integration trick. So this is just an introduction to multiple integration. You could, of course, do 3 integrals, 4 integrals, 10 integrals if you really wanted to. As long as that domain is rectangular, it's super, super easy. And if those boundaries are definable in terms of the other variables, also not too bad. Algebraically tricky, of course. But we will be doing another video on other methods of integration, in particular one that requires parametric coordinates and also polar coordinates as well. So I hope to see you in the upcoming videos. Take care.